All right, so let's begin. And first, I just want to remind everybody that the midterm is next week. It was announced on Piazza some time ago, and so hopefully everyone is ready and studying. It's going to be asynchronous. You can take it whenever you want. It'll be timed, so as soon as you start taking it, you'll have 90 minutes to complete it, and you can finish it anytime between next Monday. I think it goes live midnight Eastern time, and next Friday. And we're going to cancel class on Tuesday. So, for example, you can use class time to take it if you want. So before we begin, any questions about logistics, midterm, things like that? Okay. Is that a question? So this is sort of the halfway point in the class, and we're going to switch gears from game theory to mechanism design, basically starting today. So up until today, we've been studying game theory, by which I mean, we've been like taking games as given. Someone hands us a particular zero-sum game defined by a matrix or a particular congestion game, and we've been trying to think about how rational actors might behave in such an interaction. We've been trying to make predictions that they will play, various kinds of equilibria, Nash equilibria, correlated equilibria, and we've been trying to justify those predictions by sort of thinking about whether there are computationally plausible dynamics that might get us to those states. So mechanism design you can sort of think of as reverse game theory, in that the problem setting might specify what people's ultimate utility functions are, but the rules of the game will not yet have been defined. Like their action set won't have been defined, and the mapping between the action set and the outcome that they're gonna ultimately care about won't be defined. And the sort of thing to do to solve a mechanism design problem is to design the game, to design the action set, to design the mapping between actions and outcomes, so that when players behave as we predict that they will, and we've now developed a large collection of tools to predict what people might do in a game, the premise of mechanism design is to design the rules of the game so that when people behave rationally, they will achieve the goal that we set out. And we're gonna start by studying sort of a simple problem, and it's got sort of a fanciful premise, the house allocation problem. That's got a nice algorithm for it. But I want to point out that even though this is sort of a simple problem with sort of a fanciful premise initially, this is actually an important problem related to how kidney exchange is currently carried out, and I'll talk about that briefly. And in particular, like, we're going to solve this problem by deriving and analyzing the top trading cycles algorithm. Okay, so what is the house allocation problem? And this is called the house allocation problem because that was how Shapley and Scarf, who were mathematicians, originally defined it, and they were sort of being a little bit facetious. This is not how housing markets work, but we'll talk in a moment. This is actually, roughly speaking, how modern kidney exchange works. So the premise is that you've got these different individuals who each already have some good. Shapley and Scarf called it a house, so let's we can call it a house as well. Okay, so everyone shows up to the market and they have a house, their own house. But they have preferences over all of the goods in the market, over all of the houses. So your favorite house might not be your own house, right? And my favorite house might not be my own house. And in particular, there might be gains that could be made from trade, right? Like if you prefer my house to yours and I prefer your house to mine, then we would both be strictly better off if we traded. Okay, so the premise is everyone shows up with some good, and they've got preference orderings over all of the goods in the market. And so this isn't yet a game, right? Like there's no like actions yet, but our goal is to turn this into a game, to design some game that the players can play that will involve exchanging goods, so that both we can facilitate the coordinate the exchange of goods to arrive at some good allocation, some higher quality allocation than the one we started with. And we're going to have to talk about what that means, like what a good allocation is, and do it in such a way so that it is a dominant strategy for everyone to report their true preferences. Okay, and just let's sort of think about this for a moment. Suppose I propose an algorithm for solving this problem. So you will report something to the algorithm, like you will report to the algorithm your preferences over outcomes, okay, over goods that you might receive. And as a function of everyone's reported preferences, I will mediate some allocation. I will say, okay, here's the exchange that's going to take place. And in particular, here's the good that you are going to get. As soon as I do that, I've defined a game, right? Your action set is the set of preferences that you could report to the mechanism, right? You could report your own preferences, but also at your option, you could lie, you could misreport your preferences if that's beneficial. And there's now a mapping between these actions and outcomes, right? When everyone reports some set of preferences, the algorithm is going to choose some outcome. Okay, and you have preferences over outcomes, which house you receive. And so, as soon as we specify some algorithm, we've defined a game. And our goal here is to design a game so that, in the sense we've been talking about this whole time, it is a dominant strategy for you to report your true preferences. And let me just sort of point out why it is important to achieve both of these goals, right? And this is really what's going to separate mechanism design from algorithm design, right? So algorithm design sort of corresponds to just achieving the first goal. We want to design an algorithm that will somehow, given inputs, produce a good output. Okay, but in a mechanism design problem, which is really an algorithm design problem in a strategic setting where the inputs to the algorithm are going to be chosen by strategic agents who could misreport their own preferences, their own input, their own part of the input to the algorithm if doing so is beneficial to them. Mechanism design is different because if all we do is we design an algorithm that, given its inputs, somehow computes some good allocation, some high quality allocation as measured with respect to the inputs, then we actually have no idea whether the allocation that was computed was good, was high quality with respect to the actual underlying problem instance, right? Because the underlying problem instance is not necessarily what is given to the algorithm, right? The agents have the agency to misreport their preferences to the algorithm if that's beneficial. And so, if all we're doing is solving the problem instance we're given, but we haven't designed an algorithm that incentivizes people to report their preferences truthfully, then we might be solving the wrong problem instance, and therefore we might be fooling ourselves, right? Even though we've come up with some with some solution that is good with respect to the specified input, it might in fact be bad with respect to the true unknown input. Okay, and that's why we want to be able to design mechanisms that actually incentivize people to report their preferences truthfully, so that we can be certain that the good allocation we came up with, since we, did solve the algorithm design problem in particular in part one, actually is a good allocation, not just for the reported instance of the problem, but for the real instance of the problem, because in particular, people report truthfully. Does that make sense? It's a good time for questions about that if it doesn't, because this is sort of a basic principle of mechanism design we're going to be working with for the rest of the semester. It's algorithm design where we don't have the luxury of assuming that the instance that the algorithm is given is the correct one. We have to actually work to incentivize people to report to the correct instance of the problem to the algorithm.
A little confused why, if the algorithm is trying to give you your preference, why you would ever lie, like regardless of what the algorithm actually is.
Yeah, so the algorithm is, so that's a good intuition, and sometimes it's something we can use to actually achieve dominant strategy truthfulness. But the basic problem is, even if the algorithm, so first of all, there's this premise that the algorithm is sort of trying to give you the thing you want, which is not necessarily justified in all settings, right? The designer of the algorithm might have goals that are different from you. For example, in an auction setting, the designer of the algorithm might want an algorithm that generates high revenue, which is not necessarily aligned with your interests. And second, even if the goal of the algorithm designer is broadly aligned with the interests of the participants, like maybe the goal of the algorithm designer is to maximize social welfare, that does not necessarily mean that the goal of the algorithm designer is perfectly aligned with your particular interest, right? Because you in particular are interested in maximizing your own welfare, and that's not necessarily going to be obtained by maximizing social welfare, right? Like, it might be in this case that the good that is your favorite is also my favorite good, and it can only be given to one of us, and the algorithm is going to choose somehow to give the good to me or you or maybe somebody else. And right, no matter what happens, there's somebody who's not going to get it, and the question is, could they have misreported something so that they would have gotten it? And if so, then the mechanism is not dominant strategy truthful, and that's sort of the problem. Like if somehow the algorithm was able to simultaneously give everyone their absolute favorite choice, then you're right, it would be like pretty easy to show that such an algorithm was dominant strategy incentive compatible. Like why should you lie to the algorithm if it's going to be trying to give you your favorite choice? The problem is, like as always in game theory, we've got these like n agents whose whose goals are not all compatible with one another, right? We might all agree on what's the best object, but like only one person can get it. And so the algorithm's not going to be able to pick an outcome that is simultaneously everybody's favorite choice. And that's where the issue comes in. Does that make sense?
Yeah.
Okay.
So is 3.2 under the assumption that like all the players have like know how the algorithm works? I guess there's no like obfuscation between what the algorithm is and what the players know about the algorithm. So as if like they know how the algorithm is going to work, and even if they know, they will not change their preferences to something else so that they can get something better than what they would have gotten if they didn't know. If that makes
That's right.
sense.
So we're going to be operating under the assumption that everyone knows what the algorithm is. If there's like uncertainty about what I'm going to do, then it's hard to right, like what is our rational agent going to do? Well, you sort of have to in that case specify what exactly they know, so they could have some like beliefs about what I'm going to do, like with uncertainty, but that both would complicate things and would make our predictions a lot more brittle to like the difference between what we think they know about the algorithm and what they really know. So we're going to be sort of operating in the setting where like the actual algorithm we're going to be running, the mechanism is public, and that's the common setting. Like typically if someone's running an auction, it doesn't have like secret rules and they only tell you what the rules are after the outcome, right? You'd be suspicious if only after bids are in I sort of decided who the winner was and what they'd have to pay using secret rules that I hadn't revealed to anybody. Like at any reasonable auction, everybody knows upfront what the rules are. Does that make sense?
Yeah, that does.
Okay. Okay. So when Shapley and Scarf wrote about this, the story was house exchange, but of course this is not how housing markets are run. In particular, like this setting is sort of describing like a barter exchange market. Like I haven't mentioned money at all. People are like just trading goods, and like in general, money is a good way to mediate markets. And in fact, like in housing markets, as in many other things, we mediate them using money. You put your house on the market, there's some, market price that's established informally. The buyer gives you money, and then if you want another house, you can trade that money for a house. And fortunately, you don't have to find somebody else who would like to, move to your city, who has a house in the city that you want to move in, and work out a barter exchange. But there are things that actually do work that way. And I think the most important example is paired kidney exchange. So in the United States, at least, first of all, kidneys are important. There's, a long waiting list of people in line for kidney transplants. There's more people who need kidney transplants than there are kidneys available, and people die every week waiting for a kidney. But it's also an unusual organ in that most people have two of them and they only need one. And so you can have live donors. So, if you need a kidney transplant, then you might be able to find someone who's willing to donate their kidney to you. Now, not everybody can donate a kidney to you. There's blood type compatibilities, and even if you find someone who has a compatible blood type, there's sort of more complicated protein match compatibilities. So it's actually kind of hard to find a suitable donor. Even if you have someone who's willing to sort of undergo the ordeal of donating a kidney to you. And because of this, there's sort of a natural, there's an inefficiency here, which exchange would naturally resolve, right? So you might have somebody willing to donate you a kidney, but they cannot because of, for example, blood type incompatibility. I might have someone willing to donate me a kidney, but they cannot because of blood type incompatibility. And maybe, your donor is compatible with me and my donor is compatible with you. And so, perhaps we could arrange an exchange. Now, in principle, this is the kind of thing you could also mediate with money. Like in the housing example, you could imagine a society in which, we could raise money, either your donor could sell their kidney on the open market and my donor could sell their kidney on the open market, or maybe I just have some cash lying around and then we would buy each other's kidneys. But in the United States and in many other countries, that's illegal. So it's illegal to pay money, basically, or anything else of value for organs. And so because of this, sort of standard market solutions fail, but there's an opportunity to save many lives with effectively markets that are able to coordinate these kinds of exchanges. And that's exactly what happens. So in fact, the sort of algorithm we're going to talk about today is used in paired kidney exchange. And the premise here is that sort of the individuals coming to market are pairs of people, one of whom needs a kidney and one of whom is willing to donate a kidney. Okay, so the good that is coming to market is a kidney, and sort of the individual here is actually a donor-patient pair who are incompatible with one another. And the preferences over the goods are determined by things like blood type compatibility and sort of finer protein profile compatibilities. And it's important to be able to coordinate exchanges of this sort without using money because it's illegal in the US. And this is done. So there are thousands of paired kidney exchanges in the US every year, saving thousands of lives using basically the algorithm that we're gonna talk about today. Okay. But for the rest of the lecture, we're going to talk about houses instead of kidneys. So here's the market. Here's the model. So we've got n agents, and we're going to denote the agents by P. And each one comes to market with some good HI. And so you can read this as, house I. And we're going to be talking about a setting where agents have ordinal preferences rather than cardinal preferences. So rather than talking about like utility functions and like the utility that you would have for each house, we're going to represent your preferences just as an ordering. Okay, so you have some strict preference ordering, player I's strict preference ordering, we will write like this over all of the goods. Okay, so, if we line up all of the houses, you can rank order them from your favorite to your least favorite. And in general, if player I prefers house J to house K, we'll denote it like this, which you can read as, I guess just player I prefers house J to house K. Right, and the fact that it's a strict preference ordering just means that for every pair, either you prefer J to K or you prefer K to J. There's no indifferences. Okay, and this ranking, includes your own good. Okay, so it might be, for example, that you actually kind of like your own house, and maybe it's not your absolute favorite, but you prefer your own house to many of the other houses on the market. Okay, and our goal is, stepping into this setting to design an algorithm which will induce a game. Okay, so our goal is to design an algorithm. What are the inputs to the algorithm? Well, the inputs to the algorithm are the preference orderings. N agents will each have some preference ordering, and they will submit those as the inputs to the algorithm. Okay, what's the output of the algorithm? The output of the algorithm is the allocation. Okay, everyone came in with a good, everyone's going to leave with a good, but it might be a different good. Okay, so the output of the algorithm is some matching between agents and goods. Okay, now the agents have preferences over the goods, right? And so of course they have preferences over the outcome of the algorithm, which is going to give them a good. And so because because we have this algorithm mediating an exchange, right, taking as input preferences and outputting an allocation of the goods, when we specify an algorithm, we induce a game. Right, the action space in the game is the set of all preferences that an agent could report to the mechanism, and their true preferences specify their utility function in the game. Right, in particular, that their true preferences for every set of actions of their opponent, right, specify a preference ordering over their own action set, because every action they choose will result in some allocation, and they have preferences over these allocations. Okay, so once we specify an algorithm, then we can start talking about the resulting interaction as a game. And our goal is to design an algorithm that not only comes up with some good allocation, but induces a game such that it is a dominant strategy for every player to report their true preferences. Does that make sense? Okay, so we've said a couple times now that we would like to induce a good allocation. And so what does that mean? Like, what is a good allocation? And we're basically going to ask for something pretty weak here, which is that the allocation shouldn't be bad. So let's define a bad allocation. And informally speaking, we will say that that an allocation is bad or pareto suboptimal if it is possible to make everybody happier. Okay, if it's possible to make everybody happier compared to the allocation I suggested, then my allocation is bad in the sense that there is nobody, not even one person, who prefers that allocation over some other one. Okay, so in particular, we will say that some allocation mu is pareto suboptimal if there's a different allocation nu such that for every single person, their output in nu is at least as good as their output in nu. So there's nobody who strictly prefers mu to nu. Like at best, everyone's indifferent. And there's at least one person who's not indifferent. Okay, there's at least one person, J, such that they strictly prefer their allocation in nu compared to their allocation in mu. Okay, so we say that an allocation is Pareto suboptimal if there's some other allocation which we say Pareto dominates it, right? If there's some other allocation that Pareto dominates it, which means that in this other allocation, there's at least one person who's strictly better off, and there's nobody who's strictly worse off. Okay, so if we sort of, had a vote, like which, among all of the N agents, which of these two allocations would we prefer? We could get consensus. We could get consensus on nu instead of mu, because there's nobody who like actually strictly prefers mu to nu. Okay, right. So everyone can agree that we should not output a Pareto suboptimal allocation. Everyone would be happy to vote for a different allocation with which Pareto dominates it. And if an allocation is not Pareto suboptimal, then we'll say it's Pareto optimal. Okay, and our goal here, our sort of weak definition of what a good allocation is to just output something that is Pareto optimal, something that's not really bad, something that at least is not possible to simultaneously improve on for everyone, right? Like if we're at some Pareto optimal allocation, it might be that I personally would prefer some other allocation, but I'm not going to get consensus on that because if we move to some other allocation, there's got to be someone else who's strictly worse off. Does that make sense? Okay, so we've defined sort of our weak notion of the quality of an allocation. Let's now talk about incentives. And quite frequently in mechanism design problems, sort of as a minimal requirement, you will ask for what is called individual rationality. And here's what individual rationality means in this case, but in every mechanism design setting, there's sort of a similar definition. And individual rationality basically means that you can't be harmed by participating, right? Like in this case, it's sort of saying, well, no matter what your preferences are, okay, and no matter what other people's preferences are, at least if you tell the truth, if you report your true preferences to the mechanism, then I can promise you that you're going to be allocated something that you like at least as well as the thing you started with, right? Like the thing that you wouldn't want is that you come to the market with your house, you agree to participate in an exchange mediated by this mechanism, and then you are given a house that you like less than the one you started with, and a kidney that you like less than the one you started with would be even worse. Okay, and like if you designed an algorithm that had that property, you wouldn't be able to get anyone to participate in it. Okay, so mechanism design problems are, if you didn't require individual rationality, you could sort of often get truthfulness just by threatening people, right, with violence or something, right? But the problem is you wouldn't be able to get people to agree to participate in your mechanism. Okay, and so we're going to want to get dominant strategy incentive compatibility in a way that also guarantees that people can only benefit from participating in the mechanism compared to not participating. And that's what individual rationality is guaranteeing. That sort of in the worst case, you will walk away with your own house. I'm not gonna give you a worse good than the one you started with. Okay, is this condition clear? This is a very weak condition, but you'd hate to design a mechanism that didn't satisfy this, because then you'd find that when you launched your app or whatever, you had no users. Okay, and once we have this sort of weak individual rationality condition, which really just means it's safe to participate, we're going to ask for this stronger condition, dominant strategy incentive compatibility, which guarantees not only that people should be willing to participate in the mechanism because they can only gain, they can't lose, but actually that we can actually trust the reports that they make to the mechanism, because when viewed as a game, it's a dominant strategy for people to report their true preferences. And so, if you remember, dominant strategy truthfulness is sort of the game theoretic prediction that required sort of the fewest assumptions on rationality. Like if something's a dominant strategy, you should really play it. You don't have to think about, who else is participating in the mechanism, what they might be reporting. Like, you know that no matter what, no matter how those things shake out, like your best response is always to report truthfully. And so if we can design a mechanism that's dominant strategy incentive compatible, we have really good reason to be able to trust that the inputs that are represented to the mechanism really do reflect the true preferences in the market. Okay, so dominant strategy incentive compatibility just asks that in the game induced by the mechanism, truthful reporting is a dominant strategy. And just to sort of restate in this setting what specifically that means, what it says is that for every player I, no matter what your preferences are, no matter what everyone else's preferences are, and no matter what deviation, what misrepresentation of your true preferences you might consider reporting, if I consider the allocation that will result if you tell the truth, okay, the allocation that will result from the mechanism if you tell the truth and everyone else reports whatever they're reporting, and I consider the other allocation that you might be able to obtain by unilaterally deviating to misrepresent your own preferences, okay, then again, in all of these cases, you will prefer the good that you get in the allocation that results from truth telling compared to the allocation that you would get if you misrepresented your preferences. Okay, so because of like all of these universal quantifiers, like whatever your preferences are, whatever other people's reported preferences are, whatever clever misrepresentation you're sort of like considering, thinking about in the back of your head to report to the mechanism, it's never a good idea. Like you're always better off telling the truth than lying. Okay, and this is nothing more than the requirement that the game that is induced by the algorithm, the mechanism that we deploy, should make truth telling a dominant strategy in the sense that we've been talking about this whole class. Okay. So how are we going to solve this problem? Here's a page full of pseudocode, but it's a very simple algorithm. Let me just before we try to like parse this mess of code, like let me just tell you how it works. So imagine that the N agents are standing in a room together. Okay, they've all like come to some physical marketplace with their good. Okay, so here you are standing in this marketplace. You can look around, and there's the N goods in the market arrayed in front of you. Remember, you've got preferences over all of them. One of them is your favorite good. Okay, point to your favorite good. Everyone's going to point to their favorite good. Imagine people, the algorithm's going to construct a graph, but like imagine people like physically pointing to their favorite good. Okay, so we have these N people in the market, and each of them is pointing to exactly one good. Okay, now some of the goods might be very popular, right? There might be some good that has 10 people pointing to it. Oh, and if the good that you have, by the way, is already your favorite good, then you can point to yourself. Okay, so everyone's pointing to their favorite good, and what this is inducing really is some graph, right, in which the vertices correspond to people, and every vertex has one edge outgoing from it, right? The edge is where you're pointing. And what the algorithm is going to do is it's going to look for a cycle in this graph, right? If we can find a cycle in this graph, then that's sort of a potential trade, right? If I'm pointing at you and you're pointing at me, that means that there's a mutually beneficial trade we can work out amongst the two of us, right? Like, you can have my house and I'll have your house, and we'll both be happy because these are both our first choices. And in principle, we don't have to look for cycles of just length 2, right? I could have a cycle of 10 people. We could all give our goods to the person pointing to us in this cycle, and everybody in this cycle would be happy with this allocation because everyone would be getting their first choice. Okay, so that's what's going to happen. We're going to like look around for a cycle, And if we can find a cycle, any cycle, we will clear goods along that cycle, meaning in that cycle, everybody will get the good that they are pointing to. And because it's a cycle, everyone's happy, right? Like there's nobody, like if I have to give my good to someone else, that's only because I'm getting a better good. Okay, so we're gonna clear goods along the cycle. And those people are gonna be removed from the market because they've already cleared. They've gotten their favorite good. Okay, so suppose we find a cycle of length 10 initially. Now there's sort of 10 people who are cleared. We're going to remove them. Now there's n minus 10 people left. And we're going to do the same thing. Okay, so everyone's going to look around and they're going to point to their favorite good amongst those that are remaining. Now, there might be some people whose favorite good was amongst the 10 goods that were cleared in the first round. And so their like absolute favorite goods are no longer in the market, right? But that's okay. They're going to point to their favorite good amongst whatever's left, right? So some people might now be pointing to their second favorite good, but it is the favorite good amongst everything that's left. And we're just going to repeat this process. Okay, we're always going to look at this graph induced by everyone pointing to their favorite good amongst everything that's left. We're going to clear trades along cycles. And then we'll update the graph because when we remove goods from the market, some people, anyone who was previously pointing to that good but didn't get it, is going to have to update where they're pointing. And we're going to keep doing this until nobody's left. Okay. And the pseudocode is just explaining a little bit more formally this process. Okay, so we're going to maintain the set of people who are still in the market. We're going to call it S, right? S1 is the set of people initially in the market, and SI will be the set of people in the market at round I. And initially, it's everybody. Okay, and while there are people still in the market, we're going to construct this graph, which is just the graph that is induced when everyone points to their favorite good. Okay, so the vertex set in this graph is just the people who are still in the market. And there's a directed edge in this graph from person I to person J only if good J is person I's favorite good amongst all of the remaining goods. Okay. Then we're going to just look for cycles in this graph and we will clear trades along it, which just means if person I is pointing to good J, right, IJ is in the edge set, then person I will be allocated good J. And then we're just going to update the bookkeeping. Okay, so we're going to remove from the set of active agents, from the set of agents in the market, anybody who was involved in a cycle that was cleared this round. And that's it. Okay, so I think a pretty intuitive algorithm. Are there questions about it?
Yeah, how does this guarantee that you'll end up with a house that's better than the one that you started with?
Good question. Yeah, we're going to have to resolve all of those things. By the way, it doesn't guarantee that you're going to get something that is like strictly better than what you started with, since after all, you might have started with your favorite house. But we will want to argue that this is individually rational.
Sorry, that's what I meant.
Yes, we're going to have to think about that. Good question. Yes, so at the moment, this is just an algorithm. Like, there's no particular reason you should believe that this is individually rational or dominant strategy truthful or that it finds Pareto optimal allocations, but we're going to claim it does all of those things. But are there questions just about like what the algorithm is for now? Okay. So in fact, the first thing we want to establish is even more basic than that. Like, how do we know it's an algorithm at all? Like, how do we know it's going to actually halt and output some allocation? Because we have this like step that's like, okay, find a cycle in the graph and clear people along that cycle. But, what if there are no cycles? Right, so to show that the algorithm halts and outputs something, it is enough to show that at every round it can find a cycle. Right, because remember, how does the algorithm work? It finds a cycle in the graph and it clears that cycle and it removes any agent involved in that cycle. And a cycle will involve at least one person, right? It could be a cycle of length 1. It could be like a self loop if my own good is my favorite one amongst the ones remaining, I'll point to myself, and I might be the cycle that's cleared. But a cycle sort of, is going to have at least one person. And so if at every round I can clear at least one cycle, then the number of active agents will reduce by at least one every round, and will converge after at most n rounds. So to show this thing halts, it's sort of sufficient to show that the step at every round that involves finding a cycle never fails. But I claim that's the case. So the first claim is that in the graph that is constructed by the algorithm at every round t, this is the graph that results from everyone pointing to their most preferred good amongst the ones remaining, that there's always at least one cycle, okay? And in fact, every agent is part of the one cycle. So who can tell me why I don't have to worry about like being stuck at some round, like round 5 and not having any cycles in the graph? Why do these graphs that we're constructing always contain at least one cycle?
I feel like it might have to do with the fact that there's as many edges as there are vertices.
Yeah, so what do we know about this graph? We know that there's exactly one edge outgoing from every vertex because everyone's pointing to
Right.
exactly one vertex. So what does that tell? Why does that tell me that there has to be a cycle?
Because it's connected and it can't be a tree because it would have n-1 edges. So it has to have a cycle in there.
Yeah. So there's sort of like a simple way to see this, right? Like, imagine that you are standing on one of these vertices and you're going to take a walk. Okay, you're going to walk along the outgoing edges. So there's two things about this graph. First, you never have any choices about where to go. Right? You always have exactly one choice of where to go because there's exactly one edge leaving every vertex. And second, you never get stuck, right? Because you never, what would it mean to get stuck? It would mean that you ended up at a vertex that had no outgoing edges, but like there's always one outgoing edge. So you can always take a walk along this graph and you never have any choices and you never get stuck. Okay, so the fact that you never get stuck means there must be a cycle because you can keep walking forever, right? But there's only finitely many vertices, and so eventually you must reach a vertex that you've been to before, and that's a cycle. And the fact that you don't have any choices means that every agent can be part of at most one cycle. Okay, does that make sense? So sort of just because of how we're constructing these graphs, that everyone's pointing to exactly one vertex, we know that there has to be a cycle. And so like this concern we might have had that the algorithm just like is ill-defined, gets stuck, like we don't have to worry about that. It's like the algorithm is well-defined and will halt after at most n rounds. Okay, so let's go through like a little example just to make sure we understand the algorithm and challenge my ability to draw on this screen. So here's an instance of a problem in which there are 5 agents and 5 goods. And what you see here are the preference orderings of each of the agents. So like the way you should read this is, for agent 1, his favorite good is good 2, then good 5, then good 3, then his own good 1, and his least favorite good is good 4. And similarly, all of the other agents, also have complete preference orderings. So how's the algorithm going to work? Well, we've got a graph in which the players are vertices, 1, 2, 3, 4, 5. And they're all going to point to their favorite good. So player 1 points to good 2, that's his favorite. Player 2 points to good 3, that's her favorite. Player 3 points to good 1, that's his favorite. Player 4 points to good 1, that's her favorite. And player 5 points to good 4. Okay, so this is the graph that we get at round 1, and we find that there is indeed one cycle. Okay, so 1, 2, 3. And so we clear this. So this means that player 1 is assigned good 2, his favorite good. Player 2 is assigned good 3. That's his favorite. And player 3 is assigned good 1. That's her favorite. Okay, so we clear these guys. They're removed from the market. And so now people have to again point to their favorite goods. Okay, there's only 2 people left in the market. There's player 4 and player 5. Player 5's favorite good is still there. It was always good 4. But player 4, you know, her favorite good was good 1, which is gone now. She's now got to point to her favorite good amongst the ones that remain. That's good 5, the only remaining good in the market, because she prefers good 5 to her own good. And so we have one more cycle to clear, and we clear it. So the good that goes to player 4 is good 5, and the good that goes to player 5 is good 4. And so, okay, 2, 3, 1, 5, 4. Did I do it right? 2, 3, 1, 5, 4. Yep. So that's how the algorithm works. Okay. So is the algorithm clear? Like, does this make sense to everybody? And note that after like a cycle is cleared, we have to update the graph. Like in particular in this example, player 4 did not get her favorite good. She had to settle for her actually third favorite good. Okay, and this is why it might not be like totally obvious why an algorithm like this would be dominant strategy incentive compatible, because not everyone is getting their favorite good. And so what, you know, player 4 is now wondering to herself is whether she could have caused the algorithm to have done something differently and to actually have gotten a most preferred good, or a more preferred good at least. For example, you know, good 3 or good 1, had she reported different preferences to the algorithm, right? Then who knows? So does the example make sense to everybody?
Yeah.
Cool.
Mhm.
Question?
No, I was just saying, yeah, I'm good as well.
Great. Okay, so first let's think about the quality of the allocation found by the algorithm, and then we'll think about its incentive properties. And so the claim is that the top trading cycles algorithm indeed produces a Pareto optimal allocation on every instance. Okay, so this says nothing about incentives. It's just about the sort of input-output behavior of the algorithm, right? It says no matter what set of preferences are reported to it, the allocation that it produces will be Pareto optimal with respect to the reported preferences. And so let's approach this with a proof by contradiction. Like, suppose this weren't the case. What would that mean? Well, that means if the allocation that we output was not Pareto optimal, then it must be Pareto dominated by some other allocation. So let's say that it is. Let's say that there's some other allocation nu that Pareto dominates mu. And let's think about what nu must look like. Okay. And so the first claim I want to make is that if I look at all of the agents who happened to be cleared in the first cycle, like who were cleared in like round 1 of top trading cycles, it's got to be that they receive exactly the same allocation in nu than mu, right? Like nu and mu are different somehow, but I'm claiming like they cannot be different in the allocation of any of the agents that were cleared at round 1 of top trading cycles. Can anyone tell me why?
Because they're already receiving their the best possible preference, so they have to receive the best possible preference.
Exactly. Like what was special about the people who were cleared at round 1? Like the people who were cleared at round 1 were like super happy with their allocation. They were by construction receiving their favorite good amongst all of the goods in the whole market, because at round one, everyone was pointing to their favorite good, and the people who were cleared at round one got it. And the claim, right, if I have some other allocation that Pareto dominates mu, that means that everybody has to be at least as well off. So everybody has to be getting either the same good or a good that is even more preferred. And people who got their favorite good in mu cannot get something that is even more preferred. There is nothing that's even more preferred. So they must be getting the same good. Okay. So next, I claim that everyone who is cleared at round two of the top trading cycles algorithm, everyone who is part of the second cycle, they too must be receiving the same allocation that they do in mu, in this other allocation that, like, purportedly Pareto dominates mu, right? And this is for the same reason, right? Because, you know, let's think, like, who are the people that are cleared at round two of the algorithm? Well, there's sort of like two cases. It might be that these people were receiving their favorite good, right? Because, like, you know, what happened? At round one, everyone was pointing to their favorite good. Then we cleared some of the goods. And then, you know, some people are still pointing to their favorite good. Their favorite good was not cleared at round one. Other people are now pointing to their second favorite good because their favorite good was cleared at round one and they didn't get it. Okay. But I claim that, like, okay, given that everyone in new got the same allocation as the people who got cleared at round one in the top trading cycles, it's actually also got to be the case for people who were cleared at round two, because there's sort of only two cases here, right? Like, by the same logic, people who were getting their favorite good in mu, right? Well, there's nothing that'll improve upon that. They're still going to have to get their favorite good in anything that Pareto dominates mu. And the people who were getting their second favorite good, well, how could they improve? They could improve by getting their first favorite good, but we've already established that their first favorite good was a good that was cleared in round one, and the goods that were cleared in round one are identically allocated in nu compared to mu. So these people can't get their first favorite good in nu either. And so, since, you know, nominally we think nu Pareto dominates mu, it's got to be that they're getting exactly the same good, right? So the allocation has to be identical when we look at people who are cleared at round two as well. Does that make sense? And then the claim follows by induction, right? This is true at every level. Okay, so we've sort of proven the base case. And then the inductive case is that, well, you know, if we have that the allocation, you know, of nu and mu are identical, when we look at the subset of people who are cleared in the first k rounds of the top trading cycles algorithm, then it's got to be that it's also identical, or when we look at the people who are cleared in the first t rounds of the top trading cycles algorithm, it's got to be that it's also identical for the people who are cleared at round t+1. And this is for the same reason, right? Like, the people who are cleared at round t+1 of top trading cycles by construction are getting their favorite good amongst everything that remains after the first t rounds have completed. But the sort of inductive hypothesis here is that the allocation has been identical so far for the first t rounds. And so if your favorite good, you know, if you can't get anything that was cleared in the first t rounds of top trading cycles because it's already been spoken for, not just in mu, but also in nu, then you cannot do better than your allocation in mu, which is, by definition, your favorite good amongst everything that was remaining after the first t rounds completed. Okay? And so, you know, we have a base case for our induction, we have an inductive case, just continuing this logic through n steps of induction. We established that actually mu and nu have to be, like, actually exactly the same, like they're exactly the same allocation. And so that's a contradiction, because the claim was that nu Pareto dominated mu, and it doesn't. Okay, I try to write ta-da instead of QED at the end of these things, but I forgot on this slide. So that's the proof. Does that make sense? Does everyone understand what we proved and how we proved it? Right? And in particular, like this algorithm always guarantees for every set of inputs to produce a Pareto optimal allocation. Okay. So let's think about incentives now. And this one's easy. So I claim that the top trading cycles algorithm is individually rational. And just remember what that means. It just means that everybody leaves with a good that they like at least as well as the one they started with. Can anyone tell me why?
You could be pointing to yourself, so that would form a cycle, I guess.
Yeah, like remember, your own good is in your preference ordering, and it is allowed that you point to your own good. The only goods we ever allocate in this algorithm are goods that at some point during the algorithm you are pointing to. And by definition, you're always pointing to your favorite good amongst the ones remaining. And if you haven't been allocated yet, like by definition, again, your good remains. So the thing that you're pointing to is definitionally never less preferred than your own good. Right? It's either something other than your own good, in which case you like it strictly more, or in the worst case, it's your own good, because you're still in the market if you're like one of these vertices pointing. And if you don't like anything else as much as your own good, like the algorithm has you point to yourself. Okay, and so that's why you can never get anything that's worse than your own good from your own point of view, and so the algorithm is individually rational. Okay. And then finally, I claim that the algorithm is dominant strategy incentive compatible. Okay, so not just individually rational, but like you don't have to like do any kind of counter speculation. Like you can never do better than just telling the algorithm the truth, right? Even though the algorithm is not always going to be able to give you your first choice, you can never sort of game the system and get something even better by lying to this algorithm. And so let's prove this. And here actually, like if you view it the right way, the results quite intuitive. So let me sort of sketch the proof in a maybe more intuitive, slightly more informal way. So the algorithm, the way it really works, right, is you report some set of preferences, but like without loss of generality, we can think about the algorithm as if it really works the way I described it, where you are sort of an active participant standing in a town square, and every round are asked to point to your favorite good amongst the ones remaining. But in fact, all of that's simulated. Like all of that is simulated by the preferences that you reported. But if I let you actually point every round, that's only giving you like a richer strategy space. Like you can, in particular, implement what the algorithm would do for you if you truthfully reported your preferences by always reporting always pointing to your favorite good amongst the ones remaining. And I've only given you like extra freedom. Like now you can do silly things like, point to things that are like inconsistent with any preference ordering. So in particular, like, if I can prove that it's always in your best interest to do as you're supposed to do and always point to the good that really is your favorite amongst the ones remaining, then that suffices to prove that the original algorithm is dominant strategy incentive compatible, because it's possible to implement that strategy by reporting your true preferences. Okay, so that's like the goal. We're going to sort of imagine the players as like active participants at every round, and we want to sort of argue that it's actually a dominant strategy at every round for them to point to their favorite good amongst the ones remaining. And so let's think about this. Like what would you be afraid of? Like what would cause you to doubt that you might not want to point to your most preferred good? Like, what is the bad outcome that you might be worried about? Like what are you risking maybe by doing something other than pointing to your favorite good? Anyone want to venture a guess?
Maybe you think there'll be a lot of competition for that, and you think you try to get like first dibs on your second favorite?
Yeah, exactly, right? Like you know, it might be that your favorite thing is like also everybody else's favorite thing. You know, right? Like maybe there's these different vaccines, you know, Pfizer, Moderna, Johnson & Johnson, AstraZeneca, and like, you know, you would like the most effective one, but so would everybody else. And your concern is that if you point to your favorite thing, then you might not get it. And more than that, your concern might be that you lose out on an opportunity, right? Like maybe like today, since everyone's pointing to their favorite thing and we all agree on what our favorite thing is, if I point to my favorite thing, I'm not going to get it. But maybe like I have an opportunity to get my second favorite thing today, right? Like maybe I'm going to be the only one pointing to my second favorite thing today because everyone else is pointing to, you know, this like, you know, golden house that we all agree is the best house. And like, now's my chance. I'm going to point to my second favorite house. And if I do it today, I'm going to get it. But if I do it tomorrow, it's going to be too late because after the best good is gone, there will tomorrow be lots of competition for the second best good. Right? So like the reason you might not want to point to your favorite thing is because you're concerned about sort of missing out on some transient opportunity. Like maybe there's no way for me to get my favorite thing, but like if I act now, I can like get my second favorite thing. And if I behave honestly, you know, I'm gonna have to settle for like my fifth favorite thing. That's sort of like the thing we need to rule out. And that's the thing I wanna convince you cannot happen. Okay, and if that can't happen, then there's no reason not to point to your most preferred good, right? If there's no way to miss out on an opportunity, right? If any opportunity that is available to you today will also be available to you tomorrow, then there's no reason to sort of strategize like this. Like you might as well try to get your favorite thing, and if that doesn't work, you know, nothing lost. Anything you could have gotten today, you can also get tomorrow. Okay. And so let's think about that. Like, what are the opportunities that are available to you today? Okay, so let's imagine that, you know, everyone else has gone first. So everyone else is already pointing to their favorite good. And now here you are looking around at this, you know, partially constructed graph. All that remains is the choice of where you're going to point. And you're thinking to yourself, you know, where should I point? What are the set of goods that if you point to them today, you will get them, you know, you can get them immediately? Can anyone tell me? Like, what are the goods that, you know, I know what the rest of the graph looks like. What are the goods that I could sort of get today if I wanted? Remember that the algorithm works by clearing cycles. So if you think about how the algorithm works, the set of goods that I can get are the set of goods that form paths leading into me, such that if I follow the outgoing edge of the, you know, good all the way through, you know, I end up in a path that leads to me. right? Those are the goods I could get, because if I point to those goods, I will form a cycle that didn't exist before, going through, in particular, like me, right? Including the edge of the good that I pointed to. So let's call these goods the choice set of agent I at some particular time step. These are exactly the goods that I could get today if I wanted, right? So remember this concern I might have, right? Like, why wouldn't I want to behave truthfully? Like, my concern is that, like, my favorite good is one that there's a lot of competition for. I'm probably not going to get it if I point to it. There's something else I could get, right? Like something in my choice set, but that this thing like won't be around in my choice set tomorrow if I don't act now. And that's what we want to argue cannot happen. And so the claim is exactly that can't happen. And the way to think about that is to think about how this choice set can change over time. And so the claim is that if I have some set of goods in my choice set today, all of those goods are still going to be in my choice set tomorrow, and maybe some other goods. Okay, and so actually, like, you know, greedily grabbing something today in my choice set is not a good idea, right? Because I could, you know, greedily take the favorite thing in my choice set today. The claim is both that those things will still be available tomorrow, and that there might be other stuff that I might prefer even more, right? Because, like, you know, maybe my favorite good is also the favorite good of the owner of my second favorite good, right? So the second favorite good is not in my choice set because he's also pointing to my favorite good, right? He's not part of a path leading to me. But, you know, like maybe only my third favorite good is in my choice set. But if I'm his second favorite good, then after the first round, when maybe my first favorite good is going to be removed, he will, you know, point to me or to point to someone else in my choice set, which will add him to my choice set. Okay, so the claim is that my choice set can only grow monotonically. Nothing ever leaves it, and things might join it. And so the optimal thing to do is therefore to be patient. It's always, yeah, there's no gain and there's potentially some loss in grabbing something in my choice set if it is not my absolute favorite good amongst the ones remaining. Okay. So the reason is sort of simple to see if you remember how the algorithm works. Right? Like, how would something in my choice set be removed? Well, the only way it could happen is if one of the agents that is in my choice set was cleared, for example, or if their favorite good, the thing that they are pointing to now, was cleared. But my choice set is exactly the set of vertices that are parts of paths leading into me. And so there's no way for either of those things to happen, for either agents in my choice set to be cleared or for the, you know, their favorite goods, the things they're pointing at, to be cleared without me being cleared. Because if they're part of a path leading into me, then any cycle they're a part of is going to involve me. Okay, so like my choice set is going to remain, you know, the things currently in my choice set, the parts of the graph involved in things currently in my choice set, is going to remain static until I am cleared, because, you know, they can't form a cycle without me. Okay, and that's it. That's like the key insight, right? And that's why it's dominant strategy truthful, because the set of options that are available to you, right, your choice set, can only grow with time. And so this algorithm is set up so that there cannot be any missed opportunities. Okay. So that's it. I'll stick around for questions, and otherwise I'll see you guys on Thursday.
Thank you.
Thank you.
Yeah.